users navigation experience in a 3D virtual environment using the head-mounted display systems. The head-mounted display is a graphical visualization, is a graphical device that we usually use it to visualize a 3D virtual environment. It is often used with a tracking system to create an interactive 3D virtual world. The tracking system, we usually use this to track users' XYZ physical positions and their pitch, yaw, roll orientations. A tracking system, when we combine the head-mounted displays and tracking systems, we can convert users' movement in the real world to their movement into in the virtual world. Here is an example. An architect can use the head-mounted display system to visualize their building plan, and use the head-mounted display system so the user can view the building plan and may walk or navigate in the building plan without building in actual foundations. So here is actually a link for the video. Since my computer is not connected to the internet right now, just briefly talk about this video. At the right corner, a user is wearing a head-mounted display. The building plan is visualized through the head-mounted display. The user can see them in 3D format. And then he uses a controller to navigate in the 3D building plan. His view, what he sees from the head-mounted display is recorded in the video and the plan and played in this video. So
I got it to come up on my computer if you want to hook it up onto mine.
Yeah.
Oops.
Display. Yeah. You created that, James?
No, I did not. As much as I'd love to take credit for something that cool. Here we go. Now we're good.
So that's virtual world?
Yeah, that's like a part.
Oh, I can see by the severed hand that it's a virtual world.
Is it your hand?
I think that's a controller.
Cool.
That's pretty much about it. Thank you.
Sure thing.
As the hardware for building a head-mounted display and tracking system become inexpensive, right now the market we can buy some good quality head-mounted display and tracking systems with a few $100. The Oculus Rift company, the Oculus company, they provide the Oculus Rift. They sold it for just like $300 around. It's provide like 6 640 pixel times 800 pixels. So it's not super good, but it's a decent resolution. And Microsoft sells the Kinect One for just like around $100. It can track people's movement, facial expressions, so it will encourage more applications for virtual reality. Without any special techniques, the head-mounted display system directly converts users' movement from the real world to the virtual world. This limit the user can only travel a space in the virtual world as large as the real world space he has. Many applications may require the users can travel in the large virtual space while they stay in a small real world space. For example, a 3D gamer, they may want to use his living room as the real world track space. Then he may want to navigate in the large virtual museum. Because the living room usually is smaller than the virtual museum. If we are using the head-mounted display system, which is directly convert the user's movement from the real world to the virtual world, then the 3D gamer only can explore a small portion of the virtual museum. If the user wants to walk further, he may collide with the wall of the living room. If a few furnitures locate inside of the living room, they may collide with those furnitures too. The purpose of my study is to design a general algorithm that we can utilize the traditional redirected walking techniques, and also we want to improve it to dynamic redirected walking techniques. And the algorithm design, we want it to work with all different shaped or sized of real world spaces and virtual world spaces. The existing redirected walking techniques includes translation gain, rotation gain, curvature gain, and we use it to manipulate users' walk path in the real world without their detection. So they walk, so they can walk in the large virtual world space, and they stay in the small real world space. One of the traditional redirected walking techniques is translation gain. We define it as a quotient of a user's linear movement in the virtual world divided by his or her movement in the real world. The graph shows an example that we use a translation gain of 2 to make a user walk faster in the virtual world than in the real world to avoid a potential collision in the real world. In figure A, the user started to walk in both the real world and virtual world. At this time, he is far away from both the wall of the real world and the wall of the virtual world. However, the wall of the real world is a little bit closer to the user. So if he walks the same speed in the real world and the virtual world, he may potentially collide with the wall of the real world. So when he started to walk, we can insert a translation gain of 2, which makes him walk twice faster in the virtual world than in the real world. In the figure B, he has walked for a while. In figure C, he is finally approaching the wall of the virtual world. He sees that wall, he stopped. At the time he stopped, we kept him a good distance from the wall of the real world. In this way, we avoid a collision that could happen in the real world. Another traditional techniques for redirect walking is rotation gain. It is similar to translation gain, except that it make user rotate slowly or faster in the virtual world than in the real world. It is very useful. We often use this to make user have a good orientation in the real world. So he has more navigable space in front of him to walk in the real world. The figure shows one example. The blue geometry represents the relative size and shape of the virtual world. The real world relative size and shape is represented by the red geometry. The user's path in the virtual world is represented by the light curve. So in the virtual world, the user walk at a zigzag path. At the waypoint he turned, we can insert a rotation gain of 0.5, which make the user rotate half in the virtual world than in the real world. So if he turned 90 degrees in the virtual world, he will turn 180 degrees in the real world. So when he work along the zigzag path in the virtual world, we can make him walk back and forth in the real world. Oh, sorry. Probably no power. Another technique for the redirect walking is curvature gain. In the curvature gain is a technique that when the user walk at a straight path in both the real world and the virtual world, we are trying to rotate the virtual world around the user, and we rotate at a very small degree so the user cannot notice them, but he will react to it unconsciously. In this way, we can make him walk at a curve in the real world.
I have a question.
Okay.
While you're waiting. So for these, you said a couple times that these, you design them so that the person doesn't detect they're being redirected or something. Does that matter? Or I mean, it seems like some of these, it would be okay if the person knew they were being tricked,
Yeah.
as long as they, it's okay for them to detect they're being tricked as long as they're comfortable with it.
Yes. There are some studies they investigate how fast people can get used to those manipulations that they notice. We insert into the virtual world. For example, the translation gains, if we insert a large gain into the virtual world, people will notice it. For example, we can make him walk 3 times faster in the virtual world than the real world. He will notice it. But after he walked for a while, he get used to it, and he's still useful because he can navigate a virtual world space 3 times larger than the real world space. I will say this is very useful study. For my study, I mainly focus on the gains that within the user's detection threshold, that they don't notice those. Yes, please.
One potential problem with people noticing a lot of these manipulations is it can really hurt people's sense of verisimilitude, their immersion in the virtual environment. And so if you're setting up some kind of program where that's important, like if somebody's trying to play a game and they want to, be really into the game and not be constantly reminded, oh, I'm just playing a game, none of this is real, then if there's a lot of really intrusive alterations to what they're seeing, it can really damage that perception. So you do want to try to minimize that when possible. But there's sort of a gray area to how much are people willing to put up with for the sake of not running into walls.
Right, because, I mean, the same is true of a game, 3D game today where you're not really walking, you're pushing buttons, and you know that you're not being tricked into thinking that you're not pushing buttons, but everyone doesn't care about that because you get so good at using that alternate method to navigate that.
I'm not sure that's an entirely valid analogy. I think maybe a possibly better analogy would be if you're playing an online game and you get hit with major latency, and as a result, the game gets choppy, and that really hurts the perception, and also in the game it can get you killed. And this might be a little more akin to that because it's not just the input method, it's actually how you are perceiving the world is not conforming to expectations. But you are completely correct that for the sake of being able to navigate a small real-world space, people are probably willing to put up with quite a lot of this. So noticeable alterations.
Okay, here is a curvature game. So when the user walking straight, we rotate the virtual world graphics around him slightly. He don't notice the manipulations we insert into the virtual world, but he unconsciously react to the manipulations. So he will walk at a curve here, but he still view he's walking straight in both the real world and virtual world. I think for any of these traditional redirect walking techniques, we can insert the manipulations beyond the threshold people's perceptual threshold, and the experiments with that algorithms still useful. Just the knowledge we gain from the navigation cannot be directly, I'm not sure, but probably not directly converted to our real life experience. So we might want to have some way in the middle to convert those knowledge to our real life. We have okay. Here is a reorientation procedure. This is an explicit procedure when to stop the users when he has no space in front of him to walk in the real world. There are many ways to reset users' reorientation. One of here the graph shows one of them. The black box shows the relative size and shape of the virtual environment and the real world environment. The user starts to walk from the point of 0 and 0 in both the virtual environment and the real environment. When he walks to the point of 4 and 0, he has a lot of space in front of him in the virtual environment, but he has no navigable space in front of him in the real world environment. So at this point, if he insists to walk, he may collide with the wall of the real world. So at this point, we stop the user and ask him to turn 180 degrees in the real world. At the time he turned, we freeze the virtual world graphics. Once he completes that turn, we unfreeze the virtual world graphics so he can continue to walk in both the real world and virtual world. Since this procedure explicitly stops the users, it interrupts the user's navigation. So if we want navigation that we implicitly manipulate the user's walk path in the real world, we want to avoid this procedure as much as possible. The three traditional techniques are utilized in many different algorithms. I summarize into 4 approaches. The steer-to-center approach used curvature gains, and it used the curvature gain to always steer the user to the center of the real-world space. It assumes the real-world space is empty and with no obstacles residing inside. So its success relies on the large real-world space, but it doesn't work well with the small real-world space. The rotation gain only approach use the rotation gains. It inserts rotation gains into the virtual world when the user walking a zigzag path in the virtual world. So it can make a user walk through a large virtual space while they stay in the real world space. But the problem with this approach is that we need to have some kind of pre-knowledge about the user's path in the virtual world, because we want to insert the rotation gains at the point the user turn in the virtual world. So it also has its limitation. The translation gain only approach, it calculates the translation gain that's needed for navigate all dimensions in the virtual world. And it's pick the maximum translation gain and apply it to the virtual world. The problem is if the virtual world is really large, much larger than the real world space, the translation gain that is needed may be greater than 10, and it can exaggerate any small user's movement into a big one to be noticeable, which cause the interface not comfortable to use. The reorientation only approach does nothing to decouple the user's movement between the real world and the virtual world. It simply calls the reorientation procedure when no navigable space in front of the user. The redirect walking techniques do not always succeed. If the manipulations we insert into the virtual world are large enough, we will always detect those manipulations. A previous study suggests a general perceptual threshold exists for redirect walking techniques, including the translation gain, rotation gain, and curvature gains. But it also suggests the general perceptual threshold for those techniques are not always fixed. For example, users may be more sensitive to translation gains if they are working in a familiar virtual environment. Participants may be more sensitive to curvature gains if they have walked a straight path before the curvature gains are applied. And another study, it implements an algorithm to insert a dynamic curvature gain, a dynamic rate of curvature gains into the virtual world based on the user's walk speed. Their experiments shows that this algorithm can reduce the frequency of collisions in the real world. This study might also indicate that we can improve the redirect walking performance by using the dynamic redirect walking techniques. Since most of the traditional redirect walking techniques are designed for large real-world space, we can't find many. Very few of them work with a small real-world space, and we don't find any algorithms that work with the small real-world space and allow some obstacles residing in the real-world space. And in addition, many of them, they only use one traditional redirect walking technique, and insert a static rate of manipulations into the virtual world. So in our proposed algorithm, we trying to integrate the traditional redirect walking techniques and enhance them into our dynamic techniques. When a user is physically walking, his movement can be decomposed into a pure translation, a pure rotation, or a combination of translation and rotation, which is a natural movement. The pure translation is processed by our dynamic translation sub-algorithm, and the pure rotation is processed by our proposed dynamic rotation sub-algorithm. Currently, we haven't support the natural movement, and this is one of my future study I need to finish for my PhD study. We allow our algorithm to fail for extreme scenarios. When the user, when our algorithm fail to redirect the user to make him have a good orientation in the real world, we will call the reorientation procedure as a remedy method. We designed the simulation software to simulate the user's unconstrained navigation in the virtual world. We use this to evaluate our proposed algorithm at the development stage. When the algorithm detects the user's movement is pure translation, the algorithm will scan the path in front of the users in both the real world and the virtual world, and tries to locate the first obstacle lies in the user's path in the real world, and locate the first obstacle lies in the user's path in the virtual world. Tries to align these two obstacles together to make their collision time happen at the same time. So in an immersive virtual environment navigation, the user don't see anything in the real world. They only see the scenery in the virtual world. So he could potentially approach an obstacle in the real world, not conscious about it, and probably collide with it. Once we aligned a virtual obstacle with the real obstacle together, he may still approach an obstacle in the real world, but he sees the corresponding virtual obstacle and stop or get around. In this way, we avoid a potential collision. This algorithm is easy to implement and flexible to accommodate a few obstacles residing in the real world. When our algorithm detects user's movement is a pure rotation, we scan all the rotations around the user along his turning direction, like this. We want to look for a good rotation for the user to walk in the real world, and we use three heuristics to evaluate those rotations. When the user navigates in the virtual world, he don't see anything in the real world. But when he sees a virtual obstacle, he will stop at it. So a real world track space is only usable when it is covered with a virtual space. So we call the overlapping space as the usable track space. The first heuristics prefers a rotation that results in a large usable track space. When the user navigates in the virtual world, we think at most time he continue his current walk direction, except there was something standing in his way or he changed his target. So the second heuristic is to prefer a rotation that results a long unobstructed path in the real world. When our algorithm detects the user's movement is a pure rotation, we scan all the rotations around the user and record each rotation as 0 degree, 1 degree, 2 degrees until 359 degrees. Once the algorithm finds one rotation is good for the user to walk, our algorithm will manipulate the user's rotation to make him facing that orientation and then to walk in the real world. So we think a small rotation, which we need to manipulate the user to facing that rotation, is less noticeable than a large rotation. So the third heuristic is to prefer a small rotation than large rotations in the real world. Our simulation software display the top view of the relative size and shape of the real world and the virtual world spaces, and it also displays the user's instantaneous status in both the real world and virtual world space. We evaluate our proposed algorithm, by running simulations on a user's unconstrained navigation in the virtual world. The user's unconstrained navigation path is simulated by a random path that we generated in the virtual world space. So the simulation software also supports all kinds of shapes and size of the virtual world space in the real world space. The red geometry represents the shape and relative size we use for our simulations for virtual world spaces. In this graph, we only use a rectangle for the shape of our real world space. But in our actual simulations, we also test the real world space as a triangle or some other convex shapes. So this is the result for our simulation. It's basically say we can significantly reduce the rate of reorientation, which is the collision in the real world, compared to a naive approach. The naive approach only used the reorientation procedure. The first two columns are the range that we use to insert our rotation gains and translation gains manipulations. The third column is the rate that we reduce the collisions in the real world compared to the naive approach. The first row here is the general perceptual threshold suggested by the Stanek study. So because this is my PhD study, I still have a lot of work to work with. I want to improve my current proposed algorithm. The first one is I want to add a support to users' natural movement. Currently, my algorithm supports a pure translation and a pure rotation, which is unlikely happened in the real world because when someone moving cannot be a pure translation or pure rotation. So my proposed algorithm is only usable if we add support to users' natural movement. And I propose to reuse my current dynamic sub-algorithms. Our algorithm currently assumes the user's walking direction is consistent to his looking direction. It allows the user to have a sidewalk or walk backwards. But in some extreme scenarios, it may fail. For example, if the user close to some obstacles in the real world, he may travel in the real world and he has no navigable space to walk further in the real world, we will call the reorientation procedure to reset his orientation so he has a lot of space in front of him to walk in the real world. However, at this moment, the subject decide I want to walk backward, and then our algorithm will fail for this scenario. Second, I want to add a curvature gain to the current proposed dynamic translation gain sub-algorithm. When the user is walking straight, we can insert both the curvature gain and the translation gain. Our current translation gain algorithm flexibly align the virtual obstacle with the real obstacle to avoid a potential collision in the real world. By adding the curvature gain, we may get the user easily get around that potential the real obstacle and avoid a potential collision. When we add the curvature gain to our current proposed algorithm, we will change the user's walking direction, which might result in another potential collision happen in the real world. Since we can insert any amount of the gains within the user's perceptual threshold. So we can manipulate the user's current path in the real world into different walk path in the real world. There were some studies they researching the algorithm to predict users' future paths based on the path he has walked. So I want to reuse some of the algorithms to predict the user's future path based on a given dynamic gain application. The predicted path will be used to calculate the collision time, the time for the next collision in the real world. And my algorithm will be modified to pick one dynamic gain application that will result in the latest collision time in the real world. Currently, we use 3 heuristics to evaluate rotations in our dynamic rotation algorithm. But maybe more heuristics we can use to make our evaluation more reasonable and better performance. Since